Good morning, AP Chemistry, and this is the second video for Chapter 8. Chapter 8 covers bonding, general concepts. We did sections 1 through 3 in the first video. This is going to be sections 4 and 5, and all concept, just like the first video. This is really all concept and all verbal. So here we go. Alright, section 4 is going to cover ions. You had that before. You already know about ions. Section 5 is going to be energy effects. Section 5 is fascinating in a very conceptual manner. Talks about lattice energy because it gets kind of lengthy, but it is kind of an interesting section. Ions. We already know a couple of things that I want you to write down. First off, so here's a couple of things you need to know about ions. First off, you already know the trend. Compared to their neutral selves, cations are smaller, anions are larger. In an isoelectronic comparison, the more positive the charge, the smaller the ion. The more negative the charge, the larger the ion. The isoelectronic comparisons are those ions and possibly a noble gas that have the exact same number of electrons. So we did that in trends. Couple other things to know. Your ions are the ones that will form ionic compounds. Ionic compounds, which are also referred to as salts, are solids at room temperature. That's what RT stands for. Ionic compounds form to minimize electron-electron repulsion and maximize the proton-electron attractive force. These are ionic compounds formed from electrostatic bonding. Ionic compounds form to achieve noble gas electron configuration. That's what NGEC means. I call it NGEC, N-G-E-C, noble gas electron configuration. The metals on the left-hand side of the periodic table will lose enough electrons so that they will have noble gas electron configuration. The atoms on the right of the periodic table will gain enough electrons to make a noble gas electron configuration. You have a positively charged ion and a negatively charged ion. Opposites attract. They come together and form an ionic. Ionic bonds are formed from electrostatic attractions of closely packed, oppositely charged ions. The picture on the right is a crystalline structure of lithium fluoride. Notice that due to the electrostatic attraction, the positively charged lithium is surrounded by negatively charged fluorides, and the negatively charged fluorides is surrounded by positively charged lithiums. This is a solid at room temperature. Salt, the real salt, sodium chloride, same structure. Potassium iodide, same type of structure. Ionic bonds are formed when an atom that easily loses electrons, left side of the periodic table, reacts with one that has a high electron affinity, right side of the periodic table, positively charged on the left, negatively charged on the right. So here's where the story gets a little interesting. The ionization energy to remove the valence electron of sodium is 495 kilojoules per mole. Obviously endothermic. You are trying to remove an electron. You have to introduce energy into the neutral sodium atom to remove that one electron to make it the sodium ion. Totally endothermic. Chloride then must gain an electron. Chloride has a high electron affinity, which it should. We discussed this before. Chlorine is supposed to gain electrons to become the chloride ion. Get that from periodic trends. The electron affinity of chlorine is 349 kilojoules per mole. That, again, electron affinity is the amount of energy released when you put an electron in a gaseous atom. So this is a negative 349 kilojoules per mole. It is telling you a certain amount is released. So that's a difference of 146. The energy to remove an electron from elemental sodium is a positive 495. The energy released when you add an electron to chlorine to make it the chloride ion is a negative 349. If you add those two together, literally add them together, you would get a positive 146 kilojoules per mole, which would indicate that making sodium chloride, the salt, is an endothermic reaction. But in reality, it's exothermic. There's a discrepancy here between mathematical computation and reality. There must be a third piece to the puzzle to explain why we mathematically get a positive 146 kilojoules per mole endothermically for the production of sodium chloride, but we know in reality that it's a highly exothermic formation. They're completely different. So we're missing something, and what we're missing is the unaccounted energy that occurs when you take a positively charged ion and a negatively charged ion and bring them together. There must be an amount of energy gained or lost when you smoosh them together. Don't forget, those first two energies we discussed was merely the removal of an electron from an elemental sodium and the addition of an electron to elemental chlorine. There must be some sort of energy lost or gained when we bring the two together. That's the third piece of the puzzle. The actual bringing together of the sodium ion and the chloride ion to make sodium chloride. And that third piece of the puzzle is called lattice energy. The energy given off when separated gaseous ions are packed together to form an ionic solid. So this is the energy given off when you bring a cation and an anion together. So this is the amount of energy given off when you bring a cation and an anion together to make a solid salt. Lattice energy should be exothermic from the point of view of the system. Again, more released, the better. If you're bringing a cation and an anion together and you need an external source to hold them together, that is an unstable system and it is going to blow up in your face. If you're bringing a cation and an anion together and you're releasing excess energy, that means very little of it is being retained. That's a stable system. The more energy released, the better, because that means closer, tighter in. The cation and the anion are getting nice and snug. Ionic compounds have relatively large lattice energies because they're supposed to be getting in close. They're supposed to be forming a solid. They're supposed to be a cation and an anion and electrostatic attraction. This is something that's supposed to occur. Relatively large lattice energy means that some of them release more energy than others. Look at the previous line. More energy is released when it's a nice close fit. More energy is released when the ions are small because they get in nice and close, which is exactly what I just said. Bottom of the periodic table, left side, those are going to be really small cations, but right side at the bottom of the periodic table is going to be relatively large. So the amount of energy released is going to depend on the size of the cation and the size of the anion. All right, so one more comment about lattice energy that I want you to write down. All right, lattice energy actually has a dual role in the terms of the formation of ionic compounds. Lattice energy is the measure of stability when the cation and the anion come together to form the ionic salt. The more energy released, the better. The more energy released, the tighter the fit, the closer the cation and the anion get towards each other. Now, just a little note. If the lattice energy to bring together the cation and the anion is, let's say, negative 256 kilojoules per mole, then it would stand to reason that the amount of energy required to separate them would be equal, but going into the salt and not out of the salt. So the lattice energy has a dual role. It tells you the amount of energy released when the cation and anion come together, and also in a way tells you how much energy would be required to separate them, but the direction would be different. There is a calculation. Lattice energy is equal to 2.31 times 10 to the negative 19 joule nanometers, that is a constant, times Q1, Q2 divided by R, that's the product of Q1 and Q2 divided by R. Q1 and Q2 are literally the ion charges, and R is the distance between ion centers in nanometers. So of course, nanometers will cancel, and the charge has no units, so your lattice energy would be, of course, in the traditional units of joules. Lattice energy is equal to charge and opposite to radius, but the charge will take precedence, and I'm going to do an example. What I want you to know is the computation exists. That's it staring you in the face. You will never actually calculate lattice energy, but know the relationship between lattice energy and the charges and lattice energy and the distance of the ions. So the steps of formation of an ionic solid then, so we've got a little bit more to it than just saying, okay, let's take off an electron here, put one in here. There's a little more involved than just throwing metallic sodium in with poisonous chlorine gas. First off, sublimation of a solid metal. You have to take your sodium solid and turn it into a gas, which would take a lot of energy, boiling that baby up, and you turn it from solid to gaseous. That's sublimation, because of course sublimation means you're skipping a step. It's not going from solid to liquid gas, it's going from solid right to gas, so sublimation. Then, once you get it to the gas phase, you gotta rip out an electron, which is also endothermic. So here you've got two steps that are endothermic. Dissociation of the nonmetal. Chlorine gas in its elemental form is a diatomic. That means first off, you gotta separate them. That's an endothermic process. You have to separate two atoms of chlorine. Then you got to take one of those atoms and shove in an electron, which is electron affinity, which is exothermic. So here are four steps, three of them being very endothermic, only one of them being exothermic. Once you've prepped the sodium atom, once you've turned it into a gas form and removed an electron, once you've prepped the chlorine atom, changed chlorine gas into the chlorine atoms, and then changed it to a chloride ion, now you're ready to form the salt. And the formation of the salt must be exceedingly exothermic, huge quantity released for lattice energy for the formation of a salt. All right, a couple of examples about lattice energy. Example number 1. For example number 1, in terms of largest lattice energy based on charge, this guy will win because lattice energy is directly proportional to Q1 and Q2. So this guy is going to have the largest lattice energy. Not to mention the fact that this guy is going to be really small, so that they're going to get in relatively close. But in terms of just flat out mathematical computation, lattice energy is equal to the product of the two charges. In terms of just lattice energy and the relationship between lattice energy and the product of the two charges, this guy will have the larger product of the charges, therefore it will have the larger lattice energy. Example number 2. All right, for example number 2, of the 3 options, this guy is going to be the largest. So of the 3, calcium oxide will be the largest lattice energy due to charges. The product of the charges will be 4, this will be 1, this will be 1. That leaves us to try to figure out the sodium fluoride and the cesium iodide. Well, all right, determining which of the 2, sodium fluoride or cesium iodide, have the larger lattice energy. You can't depend on charges because they have the same product charge. Then you have to look at the actual size of the ions or the radius. The sodium ion and the fluoride ion versus the cesium ion and the iodide ion. So this is kind of a competition. Of the 2 cations, cesium is in energy level number 6. So even though it's a cation and smaller than its neutral self, it still has 6 energy levels compared to sodium's 3. So cesium is going to be a larger cation than the sodium cation. And the same with iodide. Again, like I said earlier, at the bottom of the periodic table, some of them are really super small, some of them are really fat, but that's compared to their neutral selves. You still got all those high energy levels. Iodide is going to be a larger anion than fluoride. That means in terms of size, the cesium iodide is going to be fatter, not going to get in as close together as the sodium fluoride, which are smaller ones. The cesium iodide will release less lattice energy than the smaller couple, sodium fluoride. So sodium fluoride will release. The closer they get, the more energy is released. So a couple of nice examples there. All right, achieving noble gas electron configurations, which I call NGEC for short. 2 nonmetals react. They will share electrons to achieve noble gas electron configurations. A nonmetal and a representative group metal react to form ionic compounds. Cation and an anion, or anion and a cation, respectively. The valence orbitals of the metal are emptied to achieve noble gas electron configuration. And the valence orbital of the nonmetal, you add electrons to achieve noble gas electron configuration. And show you an example. Simple example. Simple example, sodium chloride. Sodium, elemental sodium, 1s2, 2s2, 3s1, has 1 valence electron, loses that valence electron to become the sodium ion. Elemental chlorine has the electron configuration in front of you, takes you to the 3p5. The chloride ion gains an electron, Now you've got 3p6. The sodium ion has the exact same electron configuration as neon, and the chloride ion has the exact same electron configuration as argon. That is what is referred to as NGEC, noble gas electron configuration. And that's the end of that story.